Hello students, now let us see about differential pulse code modulation. Definition: in DPCM, using past sample value, the next sample value is predicted. Difference between sample value is encoded. By using redundancy, quantization can be performed with a reduced number of bits. So, bandwidth reduction is achieved in DPCM. So, this is the DPCM transmitter. M of k is the present sample and M of k minus 1 is the past sample. MQ of k is the estimated quantized sample value. So cap means it is the estimated sample value. So D of k is the difference between the present sample value and estimated sample value, and dq of k is the quantized value of the difference signal. Usually d of k is the difference sample and dq of k is the quantized difference sample value. And now let us see the operation of this DPCM. First one, quantizer. So the difference between these two successive sample value is present sample value and past sample value, and here we are going to find the difference between present sample value and past sample value. That is a step number 1. So d of k, this is the equation number 1, present sample value and past sample value. Present sample value, it is the m of k, so that the past sample value will be m of k minus 1. And next, the difference between the present sample value and the estimated value. So that is the difference between the present sample value m of k and estimated sample value, it is m of k cap. And third one, we are going to find the difference between the present sample value and the estimate of the quantized signal. Okay, mq of k is nothing but estimate of quantized signal. So now we have found, so this is the ultimate aim. So we are find the difference between the present sample and estimate of the quantized signal or sample. So why it is named as differential phase shift keying? Because this is the difference value d of k is quantized as dq of k. So first we find the difference value of present sample value and quantized sample value, that is the estimate of quantized signal value. So find the difference we found. So this encoding scheme is called differential pulse code modulation. Next one, predictor. So in the block diagram we are having the predictor is implemented with a feedback loop around the quantizer. So in that feedback loop, predictor input is denoted as mq of k and the predictor output is mq of k cap. So the difference is m of k minus mq of k cap. Now what is the quantizer output? The difference signal is quantized and it is denoted as dq of k. After the quantizer block, the quantization error q of k gets added. So dq of k value will be difference signal plus quantization noise will be added. So dq of k, that is equal to d of k plus q of k. So that the predictor input, in the predictor we are having the two input, estimate of the quantized signal and the quantized difference signal, and this will be equal to, we are going to prove mq of k. So mq of k cap, that is equal to m of k minus d of k. So how this mq of k cap, it will be equivalent to m of k minus d of k from the previous equation. So this is from this equation we found mq of k cap. So mq of k cap, that is equal to m of k minus d of k. So we are going to substitute mq of k cap, that is equal to m of k minus d of k. So this dq of k, it is as it is. Now we have just rearranged it, mq of k plus dq of k minus d of k, and dq of k minus d of k, that is equal to q of k. So from this equation we can write dq of k minus d of k, that is equal to q of k, so that this will be equivalent to q of k. Now m of k plus q of k, we can write it is that mq of k, because after every quantization, so the quantization noise will be added, mq of k, that is equal to m of k plus q of k. Now we can prove that the quantized version of m of k is mq of k. It is fed as an input to the predictor. This is the DPCM receiver block diagram. So dq of k is transmitted. First step, we found the difference value. After that, the difference value is quantized. The dq of k then transmitted through the channel. Now the dq of k value is received and it is passed. Now we can find the dq of k as well as the predictor output, that is the estimate of the quantized signal mq of k cap. So the output will be the mq of k. So mq of k is nothing but m of k plus q of k. The receiver input is dq of k, the predictor input is mq of k cap, the predictor output is the mq of k cap. What is the receiver output is mq of k. So mq of k, that is equal to m of k plus q of k, that is the message signal plus quantization noise is added. But this noise is smaller than m of k. At the receiver, the output we get the desired signal m of k plus the quantization noise, but this noise is generally much smaller than m of k. Now usually the signal to noise ratio depends on the signal power and noise power. To find the signal power and the noise power, so first we should know what is the step size del B. So it depends on the TP by MP. So TP is the peak amplitude of the difference signal and peak amplitude of the message signal. So quantization noise power is equal to del V squared by 12. Usually the signal to noise ratio is improved due to predictor gain. So predictor gain will be power of m of t divided by power of p d of t. That is a different signal. This is the message signal. Signal to noise ratio in DPCM, usually SNR value of PCM, we know that it is a 4.8 plus 6n, and it will be multiplied by the processing gain, that is the signal to noise ratio of the DPCM. Now we are going to see the slope overload noises in DPCM, and here the slope overload noise. So how to avoid the slope overload noise, that is the thing we are going to discuss here. If the message signal m of t changes so fast, the predicted signal mq of t cannot be followed. So it causes slope overload distortion. So the estimated signal should be greater than the message signal. So then only we can easily predict the message signal. So that is the concept of the slope overload noises. And d by dt of estimate of the quantized signal, this will be equivalent to number of bit size. So n minus 1 into del divided by 1 by f of s. this f of s goes to the numerator, so that it is that plus or minus f of s n minus 1 into del. And to avoid the slope overload noise, it is required the predicted signal slope should not be less than the input signal slope, so that the predicted signal slope should be greater than the message signal or input signal. So this is the predicted signal slope, it should be greater than the input signal slope. So input signal m of t max, m of t, that is equal to am into cos 2 pi fmt. When this value is maximum, because it's a 2 pi fmt, when it is a 2 pi, this is a constant, when cos 2 pi fmt is maximum in that value of 2 pi fm, so that maximum value, that is equal to 2 pi am into fm. Hence the sampling frequency is chosen to be greater than the threshold value, then only the slope or load noise can be avoided. So fs is greater than or equal to 2 pi am fm n minus 1. Thank you.